Adding and subtracting numbers in scientific notation. There are two basic rules. Number one, write as the same power of 10. And number two, add and subtract the front numbers, keep the same power of 10. We'll show you two quick examples using the rules. Then we'll talk about why the rules work, what makes them true. I really encourage you to spend as much time figuring out why the rules work as you do figuring out how to use these rules. Otherwise, you're missing a lot of the concept of scientific notation, and you'll be limited in fully understanding this concept. So here we go. Rule number one, write as the same power of 10. So do the two numbers have the same exponent? Let's see. This one's a 3, this one's a 2. So no, we need to change the smaller exponent. We have a 2 and it needs to be a 3. So how can I do that? Just add a 1 to it. What's 2 plus 1? 3. Then we use that number of 1 to tell us how far to slide the decimal of the front number to the left. So we raised the exponent by 1, so we will move the exponent to the left one spot. And we get this, 0.32 times 10 to the third. It's not proper scientific notation. That decimal's not after the first number, it's not 0, but it does let us have the same power of 3. So rule number 1 is complete. We now have two numbers that have the same power of 10. So 2.45 times 10 to the third power plus 0.32 times 10 to the third power. Now we move on to rule number 2. Add or subtract the front numbers and keep the same power of 10. So we add the front numbers of 2.45 and 0.32. Just add them together, and that equals 2.77. 5 plus 2 is 7, 4 plus 3 is 7. And then we simply add on the same power of 10, which is times 10 to the third power. So it equals 2.77 times 10 to the third power. There's your answer. Now, let's look at a subtraction problem. Adding and subtracting numbers in scientific notation, I mean, that's what we're doing, and so we've done one addition problem. Now let's look at the subtraction problem. There are two basic rules. Number one, write as the same power of 10. And number two, add and subtract the front numbers, whichever's needed, and keep the same power of 10. So rule number one, write as the same powers. Let's see, this is a 4 and this is a 2. Are they the same? No. So I need to add 2 to this one. So that makes it 10 to the fourth. And because I added 2 to it, I'm actually going to take this decimal and slide it to the left 2 spots. So I get 0.0522 times 10 to the fourth. I'll pull down my subtraction sign and I'll pull down the rest of this problem here. So what's going on? I'm done with rule number 1. We now have the same power of 10. Rule number 2, add or subtract the front numbers. Since we're subtracting in this problem, we're going to subtract the front numbers. Line up your decimals. If you need to, put some zeros in there for the placeholders. After you work this whole thing out, it's going to be, let's see, 8.6878. So now that I've subtracted my front numbers, I keep the same power of 10. I'm just going to rewrite this part here. You'll see why in just a little bit. There we go. To the fourth power. So let me fix that one. To the fourth power. We do the same rules every single time. Why does this work though? Well, let's look at problem number 1 again. You see the proper answer, and that's 2.77 times 10 to the third power. And so I'm going to erase the work, but I'm going to keep the answer. And then we're going to start looking at this problem in a different way to see why the shortcut works. Why can we trust these two rules? So here we go. I know that the answer to this problem is 2.77 times 10 to the third. Well, when you take a look at this, what does 2.45 times 10 to the third really represent? Write it in conventional notation, and it would be 2,450, because we would take this decimal and move it to the right 3 times. And what does 3.2 times 10 to the second represents? That would represent 320. So all they're trying to show you is what is 2,450 plus 320? Well, when we add these two numbers together, and if you want to use a calculator, fine, but if not, you can do it right here just as quick. We get 2,770. How can we write 2,770 in scientific notation? Let me get a red pen here. You have the decimal right here that was invisible, and we would slide it over 3 spots. So it's 2.77 times 10 to the third power. Same thing we had originally using this other method. So why do we have to change the powers to be the same power of 10? You know, why do we have to raise the second number to the same power of 10? Well, it's the only way that we're allowed to actually add these front numbers. If we don't change this to a positive 3, if we don't make that 10 to the third power and scoot this decimal over 1 spot, then we're left with it just being 3.2. And 2.45 added to 3.2 gets us 5.65. And if we call it 10 to the third, or even if we call it 10 to the second, well, I'm sorry, we don't want an answer of 5,065. We want an answer of 2,770. So it doesn't let us be able to get the correct answer by adding the front numbers or subtracting the front numbers unless they have the same power of 10. Okay, so why does this work that if I just raise this up by 1 to make it a 3, and I just slide this decimal over to the left one time, why does it work? Well, remember, 3.2 times 10 to the second power is 320. 2.45 times 10 to the third is 2,450. And when we add them up together, they get 2,770. When I raise this up by 1 and then slide the decimal back 1 spot, I get 0.32 times 10 to the third. What does this represent? Well, we would need to move the decimal over 3 spots. 1, 2, 3. So it still equals 320. See, that's the key concept there. The scientific notation, the scientific notated numbers are trying to represent a conventional number. It's just trying to show you, hey, it's 320. And if we want to do the shortcut of adding the front numbers, we need to make sure we have the same power of 10. So that way when we put 2.45 with 0.32, they're on the same power of 10, and that just lets us be able to go, oh, okay, it's 2.77. And they're both to the third power of 10. There's our answer. That's what lets us be able to add those front numbers. If you don't do that, you'll get a wrong number every single time.